Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Please allow me to reintroduce myself. I'm Philip Emeagwali. I began supercomputing at age 19 on June 20, 1974 in Corvallis, Oregon, USA. Back then, there was no computer in my country of birth, Nigeria. In 1974, the parallel supercomputer, that's the precursor of the world's fastest computer, was mocked and dismissed as science fiction. Parallel processing was an unproven technology that couldn't be harnessed to achieve the world's fastest computer speeds of a vector supercomputer. The unproven technology couldn't be used to solve the most compute-intensive problems, such as executing computational fluid dynamics codes, including executing high-resolution global climate models, and doing so to foresee otherwise unforeseeable long-term global warming. In the 1980s and earlier, everybody ridiculed parallel supercomputing. The technology was mocked and dismissed as unproven and as a tremendous waste of everybody's time. My contributions to the development of the computer were these. I was in the news for becoming the first person to use the slowest processors in the world to discover the fastest computing in the world and solve the most compute-intensive problems in the world. My scientific discovery, called fastest computing, occurred at 15 minutes after 8 o'clock in the morning of July 4, 1989, in Los Alamos, New Mexico, USA. Briefly, I discovered how to execute the world's fastest computing with the world's slowest processors. My discovery of the fastest computing revolutionized the essence of both the computer and the supercomputer. The world's most powerful supercomputer cost $1,250 million, and it costs 40% more than the mile-long Second Niger Bridge at Onitsha, my ancestral hometown in Nigeria. The supercomputer is used to solve the most compute-intensive problems in mathematics, science, and engineering. Without supercomputing across millions of identical processors, these grand challenge problems will be impossible to solve. A new technology for fastest computing creates new sciences. The world's fastest computer opened the door to unexplored areas of mathematics, physics, and computer science. The diverse applications of the supercomputer range from all exploration to a surer prediction of global warming. The earliest experiment across a massive ensemble of processors in which a grand challenge problem was solved occurred at 15 minutes after 8 o'clock in the morning of the 4th of July, 1989 in Los Alamos, New Mexico, USA. That first experiment led to my signature invention, which is the new knowledge that powers the world's fastest computer and enables it to solve problems that were once impossible to solve, and solve them in parallel and across my global network of processors that outline and define my new internet. Shortly after my experiment of July 4, 1989, I was in major US newspapers for winning the highest award in supercomputing. That first experiment provided the blueprint on how to parallel process and do so across a new internet. That never before visualized internet was a vast ensemble of 65,536 off-the-shelf processors that tightly encircled a globe. Those processors were coupled and shared nothing. My 2 raised to power 16 identical processors communicated synchronously and computed simultaneously, and did both to solve the most compute-intensive problems in the scientific and engineering worlds. In an email, a 12-year-old writing the biographies of famous computer pioneers asked me, "How are supercomputers used in Kuwait?" The supercomputer market is valued at $45 billion a year. The energy and geoscience industries buy 1 in 10 supercomputers. The Marguard oil field in the desert of southeast Kuwait was discovered in 1937. The Marguard oil field contains up to 72 billion barrels of recoverable crude oil reserves. The greater Marguard oil field is the world's largest sandstone oil field. The Marguard oil field is declining at 14% per year. Fastest computing, executed across billions of processors, is used to recover about half of the crude oil reserves inside the Marguard oil field. In 1989, I was in the news for discovering how the slowest processors in the world could be harnessed as the world's fastest computer and used to discover and recover otherwise elusive crude oil and natural gas. The parallel supercomputer became known to a broader audience after my scientific discovery of the 4th of July 1989. That discovery yielded the world's fastest computer speeds that I recorded across the world's slowest processors, and recorded while solving one of the world's most compute-intensive problems. I arrived at that frontier of knowledge by contributing to the knowledge discovered by research scientists whose names were lost in the midst of time. In the past 100 years, the population of the scientific community has grown by 1,000-fold. A century ago, there were only 1,000 physicists in the world. Today, we have 1 million physicists in the world. We could say the same of mathematicians. The body of knowledge, now described as information and communication technologies, has grown exponentially since the 1940s. The parallel processing problem, which I solved in 1989, was then classified by the US government as the grand challenge problem of supercomputing. My solution of that compute-intensive problem traversed extreme-scale partial difference equations of computational linear algebra, traversed partial differential equations of calculus, traversed large-scale computational physics, and traversed the supercomputing across up to 1 billion processors that made the news headlines because I parallel processed to solve the most difficult problem in mathematical physics. I solved that problem across a new global network of off-the-shelf processors that outline and define a never-before recognized internet. That grand challenge problem was far more complex and compute-intensive than the calculus problem that Isaac Newton solved 3 centuries and 3 decades ago. It's more difficult to invent new calculus than to understand the calculus in textbooks. For that reason, contributions of new partial differential equations to the existing body of mathematical knowledge is more valuable than the mastery of mathematical methods. Nonetheless, the mastery of mathematics and physics is always a precondition for the invention of new partial differential equations as well as the world's fastest computers for solving them. As a computational mathematician, I invented discrete approximations that honor both the governing partial differential equations of calculus and their underlying physics. My contribution of the world's fastest computing to mathematics and physics is used to extract crude oil and natural gas that are buried up to 7.7 miles deep and formed up to 541 million years ago. An oil field is about the size of Abuja, the capital of Nigeria. An oil field is a mixture of different materials which has properties that vary from point to point. Often the properties may not have the same value along perpendicularly different directions. The value along the z direction might be different when compared to those along the x and y directions. Such differences, called heterogeneities and anisotrophies, make my supercomputer model more complex. As an aside, Isaac Newton wasn't a scientist. The term scientist was coined about 1.5 centuries after Isaac Newton died. Instead, Isaac Newton described himself as a natural philosopher, not as a mathematician or a physicist. Contrary to what is widely believed, Isaac Newton devoted most of his careers to researching occultism, not to searching for new laws of physics. Looking back retrospectively, there are 1,000 times more geniuses today than 1 century ago. Yet in the 1940s, the likes of the physicist Albert Einstein couldn't parallel process, in part because the technology and the technique were then unknown. For those reasons, they couldn't accurately solve an initial boundary value problem of mathematical physics, such as global climate modeling, to foresee long-term global warming. Global climate modeling is the most important problem in computational physics. If I can travel back in time to 3 centuries and 3 decades ago to Cambridge, England, I will explain to Isaac Newton how we use the system of partial differential equations of calculus that encodes the second law of motion of physics and use them to model the transport of pollutants through a groundwater aquifer. Solving this difficult problem of mathematical physics demands the simulations of a complex set of biogeochemical reactions that in turn is coupled with the simulations of the multi-phase flows of air and water. I will explain to Isaac Newton how the compute intensiveness of modeling groundwater aquifers and production oil fields increases when their solutions are governed by partial differential equations. Such equations account for multi-phase fluid flows and give rise to mathematical objects called tensors that represent heterogeneous aquifers that are characterized by anisotropic peak hydraulic conductivities. I will explain to Isaac Newton that a tensor is similar to a vector, but a tensor is more general than a vector. The array of components of a tensor are functions of its spatial coordinates. Finally, I will explain to Isaac Newton how and why many mathematical models are multi-physics and multi-scaled. The reason is that some phenomena are governed by different laws of physics and chemistry and occur over wide-ranging temporal and spatial scales. The science of today was the science fiction of Isaac Newton. Back in 1989, I was in the news because I was the first person to understand how to solve the most compute-intensive problems in supercomputing. I discovered how to tackle the world's most compute-intensive problems in algebra, calculus, and physics. I discovered how to solve them across a new internet. That's a new global network of 65,536 off-the-shelf processors and standard parts. That contribution to mathematics was the reason I was the cover story of the top publication in the world of mathematicians, namely the May 1990 issue of the Siam News. I was the cover story because the foremost mathematicians in the world were being informed that I discovered how to solve initial boundary value problems governed by partial differential equations that encoded the laws of physics. I discovered how to solve the most compute-intensive problems and how to solve them not merely on the blackboard or even on the motherboard, but across an ensemble of up to 1 billion processors that equidistantly surrounded the globe, and did so in the manner the internet circumscribes the earth. My discovery made the news headlines because in the 1980s, nobody else could execute the most compute-intensive global climate models and compute with the slowest processors in the world, and do so while recording the fastest speeds in supercomputing. The global climate model must be parallel processed to enable the climatologists to foresee otherwise unforeseeable long-term global warming. In 1989, I was in the news because I discovered the fastest computer speeds that are possible and discovered how to compute across a new ensemble of up to 1 billion processors that surrounded a globe, and did so just as the internet encircled the earth. I began supercomputing on June 20, 1974 at age 19 at 1800 Southwest Campus Way, Corvallis, Oregon, USA. On my 16th anniversary of supercomputing, I was credited in the June 20, 1990 issue of the Wall Street Journal for discovering how to compute together and how to communicate at once and how to do both across a new ensemble of 65,536 processors, and how to compute at the fastest recorded speed, and do so to tackle the most compute-intensive problems. Such difficult problems could only be solved by dividing them into billions of lesser compute-intensive problems that in turn could be solved only by a one problem to a one processor mapping onto a network of millions of processors. This problem to processor mapping is the substance of how the first supercomputer that computes fastest across the slowest processors is used to tackle the biggest and the most intractable problems in the mathematical sciences. As a research supercomputer scientist who came of age in the 1980s and in the USA, my goal was to contribute new knowledge, namely the speed and speed up across up to 1 billion processors. My record speed in supercomputing of July 4, 1989 was new knowledge that was used to actualize the world's fastest computing across over 10 million processors. My discovery was a milestone in computer history. My invention turned parallel computing from fiction to fact. In the 1970s and 80s, the world's fastest computing across up to 1 billion processors and its use to get more accurate solutions of initial boundary value problems governed by partial differential equations of calculus and physics was classified as a grand challenge problem. It was so called for a compelling reason. In the 1980s, attempting to harness an ensemble of 64 binary thousand processors and use them to emulate a virtual supercomputer was as difficult as attempting to make science fiction become reality. That grand challenge was the reason the farthest frontier of the massively parallel supercomputer had only one permanent resident. I was that permanent resident of the then unknown world of the world's fastest computing across up to 1 billion processors. In 1989 and in the USA, I was in the news because I witnessed the first dramatic upgrade in our understanding of the computer of tomorrow, not as a new computer per se, but as a new internet de facto. The computer will become the internet and vice versa. It's impossible to say exactly how the world's fastest computers are used. Some supercomputers, such as those used to simulate the shock waves emanating from the explosions of nuclear bombs, only exist off the record. The supercomputers for nuclear labs are manufactured without serial numbers, and oil companies protect their supercomputer simulations as trade secrets. I was coerced to sign non-disclosure agreements that prevented me from telling you everything that I know about the world's fastest computing. In the 1980s, the massively parallel supercomputer was only available to a few dozen scientists that worked within the US Federal Nuclear Research Laboratories. Today, such supercomputers are available to everyone. I was the only full-time programmer of the 1980s of the most massively parallel supercomputers ever built. That was how and why I became known as a supercomputer scientist. In an email, a 12-year-old writing the biographies of famous mathematicians and their contributions to the development of the first supercomputer that computes the fastest across the slowest processors, asked me, "How do you become a supercomputer genius?" You become a supercomputer genius by first deeply understanding the difficult mathematical problems that you must solve, and by deeply understanding how you must divide the most compute-intensive problems into up to 1 billion lesser challenging problems, and knowing how to solve them with a unique one processor to one problem mapping that preserves nearest neighbor nearness, and understanding how to solve such problems across the up to 1 billion processors that outline and define the massively parallel supercomputer. That supercomputer genius must be a polymath or a jack of several sciences. That supercomputer genius must be at home at the frontiers of knowledge in mathematics, physics, and computer science. The supercomputer genius must understand his computing machinery and know it forward and backward and even sideways. The supercomputer genius must be the first person to understand how to compute at speeds that were considered impossible, and compute to address some of the world's biggest challenges, and compute in a breakthrough way that's ranked as a milestone and that changed the way we think about the modern computer and the fastest supercomputer. It took me 16 years on the world's fastest computers to discover that I could compute at the world's fastest speeds and do so across the world's slowest processors, and do so to solve the most compute-intensive problems in science, engineering, and medicine. The world's fastest computing that's executed across 1 million coupled processors is the central knowledge that must be used to foresee the otherwise unforeseeable spread of contagious viruses that occurs during a once-in-a-century global pandemic such as COVID-19. My contributions to the development of the first supercomputer, as it's known today, made the news headlines because I discovered that parallel processing will become the vital technology that will be used to manufacture the world's fastest computers. I didn't merely discover the world's fastest computing across one binary million email wires, nor did I invent the technology by luck or serendipity. I discovered the world's fastest computing because I deeply understood the underlying mathematical physics that defined the compute-intensive problem that must be parallel processed across up to 1 billion processors. In 1989, and in the USA, I was in the news because I discovered how to solve the most compute-intensive problems in mathematics and physics, and how to solve them in parallel and across my new internet that was a new global network of 2 raised to power 16 or 65,536 coupled off-the-shelf processors. Those processors were equal distances apart and shared nothing but we are in dialogue with each other. I provided the complete details of my supercomputing inventions and did so across 1,000 podcasts and YouTube videos. I posted the most YouTube videos, YouTube lectures, because I have the most knowledge in the field of supercomputing. My YouTube lectures encapsulated the knowledge of mathematics, physics, and computing that I gained from nearly 50 years of fastest computing that began on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, USA. I had to be a polymath, not merely a mathematician, to work alone and solve the most difficult problem in supercomputing, which traversed half a dozen frontiers of scientific knowledge. In contrast, American scientists work in large teams. A person that was aided by 100 scientists might only understand 1% of the work and therefore cannot give an impromptu interview or deliver an on-the-spot lecture and do so without the support of PowerPoint photos. Having a supercomputer is one part of the equation for solving the most difficult problems arising in supercomputing. Only a polymath can translate and solve the toughest problems at the crossroads where new mathematics, new physics, and new computing intersect. The extra knowledge that gave me an edge over other mathematicians, physicists, and computer scientists was that I was the first person that could translate some laws of physics into a system of partial differential equations of calculus. The partial differential equation is the pillar on which the supercomputer rests. I converted those equations into their algebraic approximations. That is a system of partial difference equations of algebra. Finally, I invented algorithms and email primitives that are my final step-by-step instructions for my world's fastest computing. Each processor must execute in lockstep my programmed instructions and execute within and across millions of processors that shared nothing. Those were the mathematical conditions for inventing the world's fastest computing. I used my new supercomputing knowledge to solve the most difficult problems and solve them across the world's slowest processors. My contribution to supercomputing knowledge was in the news shortly after its discovery at 8:15 in the morning on July 4, 1989 in Los Alamos, New Mexico, USA. I invented the world's fastest computing, the way Bob Marley writes songs. The toughest problems in supercomputing traverses mathematics, physics, and computer science. For that reason, a supercomputing genius must be a polymath. The supercomputing polymath left his or her specialty for several years and left it to conduct research in mathematics or physics or computer science, and do so to gain a different perspective from each field. In my quest for how computing across processors powers the world's fastest computers, I left the frontier of knowledge of mathematics, known as partial differential equations and computational linear algebra, for the frontiers of knowledge of physics, known as fluid dynamics. I did so to become a mathematical physicist who investigated how to solve the most compute-intensive problems that arise during geophysical fluid flows. Supercomputing problems, such supercomputing problems include forecasting and hindcasting the global scale motions of fluids, that is, liquids and gases, that enshroud the Earth. Geophysical fluid motions include subsurface, multi-phase fluids flowing across anisotropic and heterogeneous porous media and flowing up to 7.7 miles or 12.4 kilometers below the surface of the Earth. Geophysical fluid dynamics, fluid motions, include centuries-long global climate modeling, executed to foresee otherwise unforeseeable global warming. After a decade following 1974, I left mathematical physics for the frontier of knowledge of the then unexplored field of the world's fastest computing across the world's slowest processors. Looking back and using a metaphor, I learned that if you've never left your house, it's impossible to have ever seen your entire house. In 1989, I commanded and controlled more supercomputing power than any person that ever walked on planet Earth. I understood the world's fastest computing deeper than the armchair theoretical physicist and deeper than the mathematician who never left his blackboard for the motherboard that occupies the footprint of a football field. I'm a polymath who sojourned from mathematics to physics to computer science and did so across half a century to leave behind a legacy of 1,000 podcasts and YouTube videos. Famous scientists who came of age after the mid-20th century were obliged to leave as their legacy a series of videotaped lectures. Each lecture must describe their contributions to mathematics or physics or computer science. Albert Einstein shared about 10 videos. I shared 1,000 videos in YouTube, each up to 4 hours long. My 1,000 podcasts and YouTube videos were the culminations of half a century of painstaking research that began on June 20, 1974 in Corvallis, Oregon, USA. Listening to only one of my podcasts instead of watching my 1,000 YouTube videos is by being misled by a single still frame photograph. It's like writing a book review after only reading one page of a 1,000-page book. My 1,000 YouTube videos permit their viewers to approximate my lecture experiences, but watch them without their visceral impact. As the first supercomputer scientist who came of age in the 1970s, it was imperative that I followed a different path to the frontier of human knowledge of the world's fastest computing across the world's slowest processors. At that supercomputing frontier, new partial differential equations of calculus and large-scale algebra intersected, and new algebra and fastest computing intersected. I visualized my world's fastest computing as occurring around a new internet that was a small copy of the internet. Both internets encircled a globe in the 16th and 3rd dimensions of hyperspace, respectively. My scientific discovery of the world's fastest computing occurred at 15 minutes after 8 o'clock in the morning of July 4, 1989 in Los Alamos, New Mexico, USA. That new knowledge was my breakthrough answer to a perennial big question that appeared in a science fiction story published on February 1, 1922. 67 years Later, I was in the news as the African genius that won the highest award in supercomputing. Computer scientists call my award the Nobel Prize of Supercomputing. I won that top supercomputer award in 1989 because I discovered how to turn that science fiction story of 1922 to a reality that's a new spherical Ireland of 64 binary thousand off-the-shelf processors that could be harnessed and used to solve the most difficult problems in science, engineering, and medicine. The poster boy of the 20 most difficult problems is computing at the world's fastest speeds and doing so while executing large-scale, high-resolution global climate models and executing them to foresee long-term global warming and to find answers to previously unanswerable questions and create new branches of human knowledge, such as the world's fastest computing across the world's slowest processors. The indication of my contributions to the development of the fastest computer is not merely that I recorded the fastest computer speed, but that I did so via my new paradigm of communicating and computing across an ensemble of millions of processors, rather than via the old paradigm of serial supercomputing or vector supercomputing within one fast processor. I was in the news in 1989 because my recording of the world's fastest computer speed that I measured across the slowest processors in the world was a technological feat considered impossible at that time. My discovery of an alternative way of recording the fastest speeds in computing inspired the change in the way we look at both the computer and the supercomputer, and inspired the radical departure from vector computers that solved one problem at a time and was the size of a refrigerator to the first supercomputer as it's known today, that solves millions of problems at once and that occupies the space of a soccer field. And it costs the budget of a small nation, or $1,250,000,000. Because the fastest computers in the world are precious. Each is protected by armed guards and is classified as a state secret. For economic and national security reasons, the US barred China from buying American processors and using them to power Chinese supercomputers. China understands that dominating the $45 billion a year supercomputer market is its stepping stone to dominating the globe in scientific discoveries and technical breakthroughs that are the preconditions to becoming the world's superpower. In the 1970s and 80s, my scientific search was for answers to the most important questions at the crossroad where new mathematics, new physics, and the world's fastest computing intersect. My quest demanded that I look beyond the frontiers of mathematics, physics, and computer science. I did so because I realized that the discretization of the partial differential equations of calculus is an inadequate answer to the big question of how do mathematicians solve the initial boundary value problems of mathematical physics. Such problems govern the high-resolution global climate model that must be used to foresee otherwise unforeseeable long-term global warming. Mathematical knowledge alone was an inadequate answer to big questions just as the technological knowledge of the fastest computing across the slowest processors is also an inadequate answer to the science fiction question of how to design, manufacture, and program the ultimate supercomputer of forthcoming centuries. Looking back to 1974 and 15 years onward, those that insisted that I remain in only one field, such as mathematics or physics or computer science, were standing in the way of my invention of the first supercomputing across the world's slowest processors. Fastest computing was not entirely within mathematics or physics or computer science. I discovered it at their intersection, and did so when the naysayers were standing in the way of the critical and enabling parallel processing technology that now underpins the world's fastest computer, and that would allow faster computers to emerge from an ensemble of millions of slower processors. Being at the frontiers of knowledge of the fields of physics, calculus, algebra, computer, and internet sciences is the minimum requirement to becoming the first person to solve the most compute-intensive problems central to supercomputing. Abstract mathematical physics is the most recurring decimal inside the billions of processors that define and power the world's fastest computers. Therefore, if I didn't understand the computational physics or the abstract calculus or the large-scale algebra which I was inventing on my blackboard, and which I was supercomputing on and across my 64 binary thousand processors, then my chances of discovering how to parallel process and do so to compute at the fastest recorded speeds demanded that I achieve a one problem to one processor correspondence for my 65,536 initial boundary value problems of extreme scale computational physics. That one-to-one correspondence was the mathematical precondition to solving the parallelized problems at once. Without that one-to-one correspondence, my chances of recording the fastest computer speeds were as good as having 65,536 monkeys typing on as many computer keyboards, and then expecting their asynchronous typing to record a 64 binary thousand-fold increase in never-before recorded email and supercomputer speeds. In retrospect, the reason I was the lone programmer of the most massively parallel supercomputers of the 1980s was that I was the only person that could execute fastest computing across billions of processors and solve the once impossible to solve grand challenge problem of supercomputing. I solved that grand challenge problem because my confidence came from knowing who I was, what I was doing, and who I am. My first night in the USA was spent alone in 36 Butler Hall, Monmouth, Oregon, and on Sunday, March 24, 1974. I was then 19 years old. I was the supercomputer scientist in training that emigrated from Onitsha, Nigeria, a commercial city in the heart of sub-Saharan Africa. I came alone to Oregon in the heartland of the Pacific Northwest region of the USA. I came and became the mathematician that discovered new mathematical knowledge. Over the following decade and a half, I grew and evolved and found myself beyond the farthest frontier of high-performance computational mathematics. Computing across millions of processors was the jagged, multidisciplinary frontier of supercomputer knowledge. For the 16 years between my supercomputer research in Corvallis, Oregon, and Los Alamos, New Mexico, I felt like an explorer that walked alone with a dim lamp and along a small road that was the holy grail of the world's fastest computing. During my 16-year-long quest for how to harness a million processors and use them to power the world's fastest computers, I learned to distinguish between experiment and theory, between theory and discovery, and between fact and fiction. And I learned to know for the first time that a theory is an idea that is not positively true. In the decade that preceded 1989, I invented supercomputer algorithms grounded on mathematical equations from the laws of physics. Specifically, I invented partial difference approximations of large-scale computational linear algebra that approximated partial differential equations of calculus that encoded the second law of motion of physics that was discovered 3 centuries earlier. I invented equations of mathematics grounded on the laws of physics, and I heard and trusted my inner voices that were almost drowned in a cacophony of secondary voices. In 1989, I was in the news for discovering that the slowest processors could be used to solve the biggest problems arising in mathematics and physics and find their answers at the fastest speeds. The fastest computer is why you know the weather before going outside. Briefly, my mathematical quest was to find how to solve the toughest problems that arise at the intersection of calculus and large-scale geophysical fluid dynamics, including solving the initial boundary value problems known as global climate modeling and petroleum reservoir simulation. As a research mathematician who came of age in the 1970s and 80s, who is at the frontier of physics and supercomputing, my grand challenge in those 2 decades was to be the first person to understand how to solve initial boundary value problems at the intersection of partial differential equations that are encoded in some laws of physics. My contribution to mathematics is this: I was the first large-scale computational physicist and the first person to solve initial boundary value problems across a new internet. My new knowledge of the world's fastest computer is used to understand the spread and treatment of COVID-19. I visualize my internet as a new global network of the slowest processors in the world. I theorized that my internet could be harnessed and used to execute the fastest computing in the world. For 16 years, following June 1974, and from Corvallis, Oregon, to Los Alamos, New Mexico, the naysayers forced me to conduct my fastest supercomputer research alone. In the early 1980s, I was often disinvited from giving supercomputing lectures, and only disinvited after they discovered that I was black and African. I invented the 9 Philip Emeagwali equations, and I did so from scratch, or first principles, called the second law of motion of physics. My system of 9 coupled nonlinear and time-dependent partial differential equations governs initial boundary value problems that must be used to model the subterranean motions of crude oil, injected water, and natural gas flowing up to 7.7 miles or 12.4 kilometers deep and flowing below the surface of the earth and within an oil-producing field that's often the size of Ibadan, Nigeria. The world's fastest computer is like a telescope that's used to peer inside the human DNA, or 7.7 miles deep inside an oil field. My quest was for new knowledge that will enable me to parallel process computational fluid dynamics codes used to model the weather of up to 7.7 miles or 12.4 kilometers below the surface of the earth. This grand challenge problem is the poster girl of compute-intensive physics. In 1989, I was in the news as the first person to discover how to divide the biggest problems in mathematics and physics and divide each grand challenge problem into up to 1 billion lesser challenging problems that can then be solved across as many processors or with a one problem to one processor correspondence. For my specific experiments across the world's slowest processors, in which I recorded the world's fastest computing and did so at 8:15 in the morning of July 4, 1989, I visualized my 65,536 equal reservoir models as oil field number 1, oil field number 2, all the way to oil field number 65,536. I visualized a one oil field to one processor correspondence. I executed that one-to-one mapping between those oil fields and as many processors that shared nothing. My processors were equal distances apart, and each processor operated its operating system. My processor-to-processor email directions were that oil field number 1 is directly and bidirectionally connected to oil field number 2. Oil field number 2 is directly and bidirectionally connected to oil field number 3. I continued to directly and bidirectionally connect all nearest oil fields. But the last, or oil field number 65,536, is directly and bidirectionally and circularly connected to oil field number 1. My one-to-one mapping was at the core of my discovery of the world's fastest computing as we know it today. I was in the news because I discovered how to hindcast the weather 8 miles inside the earth. The polymath knows more sciences than the mathematician and understands a priori that the calculus that governs the short-term weather below the surface of the earth have identical partial derivative terms as the calculus that governs the long-term weather above the surface of the earth. The reason for the mathematical similarity is that both are computational fluid dynamics problems grounded on the partial differential equation of calculus and on the partial difference equation of linear algebra, and in part because the dependent and independent variables are similar. Accurate weather forecasts are generated with supercomputers and are critical to protecting life and property. Back from September 1, 1981 through August 1986, I lived a 15-minute stroll from the Greymax Heliport building in Silver Spring, Maryland. The Graymax building was the then headquarters of the U.S. National Weather Service. During those 5 years, and from Mondays through Fridays, I stopped each morning and spent 5 hours with hydrologists and meteorologists. During my 5 years with those research meteorologists, I was inspired to look into the finite difference discretizations of the primitive equations of meteorology that were used by the U.S. National Weather Service and used to forecast the weather. In the early 1980s and in College Park, Maryland, I discovered that the grand challenge problems of hindcasting the weather underneath the earth and forecasting the weather above the earth are governed by initial boundary value problems that look similar. Yet, for a century, the geologist and the meteorologist was not aware of that similarity. That ignorance robbed both fields the benefit of cross-fertilizations of their discoveries. The computational fluid dynamics model that I executed across my ensemble of 65,536 processors was the most difficult problem in supercomputing. It was an initial boundary value problem posed across a new internet that I defined as a new global network of 65,536 processors that shared nothing. In the 1980s, the US government classified this problem as a grand challenge, and did so in part because its solution demands a $1 billion supercomputer that occupies the footprint of a football field and that then existed only in the realm of science fiction. As a mathematician and physicist who grew over the 1970s and 80s to become the first programmer of the first supercomputer as it's known today and as it's expected to be known tomorrow, I know from first-hand experience that it was harder to solve an initial boundary value problem and solve it across millions of processors than to merely pose the problem on one blackboard. The former is the solution discovered by the polymath. The latter is the question asked by the mathematician. It's easier to ask a question than to answer it. As a mathematician searching for new calculus and new algebra, I looked for and made use of patterns and structures from disparate fields of human knowledge. A few years ago, I posed a question meant for the Joint Admissions and Matriculation Board of Nigeria, or JAMB for short. What is the importance of physics in the development of Nigeria? The supercomputer must be used to tackle the biggest and the most difficult problems of tomorrow. In the 1980s, the precursor to the world's fastest computer was confined to crunching massive amounts of data from large-scale computational fluid dynamics simulations. My computational physics across millions of processors must be used to locate energy deposits. Please allow me to quote myself from a lecture that I delivered in the 1980s. In petroleum reservoir simulations executed for the oil fields of Nigeria, the dependent variables are the compressibility of the fluids, pressure, fluid partial molar volume, saturation, phase partial molar volume, total fluid velocity, as well as source and sink terms. Such terms include water injection wells and crude oil and natural gas producing wells. To derive the system of equations of extreme scale computational linear algebra within compositional reservoir simulators used for enhanced oil recovery processes that must be parallel processed across an ensemble of processors demands that the governing system of coupled nonlinear time-dependent and three-dimensional partial differential equations be discretized with one of three finite difference techniques. The first technique is known as the implicit pressure, explicit composition method. This finite difference approximation has small time steps and the least computation time per time step. The second technique is known as the implicit pressure and saturation method. This finite difference approximation is more stable and handles larger time steps. The third technique is known as the fully implicit method. This finite difference approximation is the most stable and handles the largest time steps. I became a supercomputer scientist after putting in my time in grade. My due diligence that yielded the world's fastest computing occurred daily, and it occurred during my half-century of supercomputing that was onward of June 20, 1974 in Corvallis, Oregon, USA. I'm the subject of school essays because I was the first person to figure out how to solve the most difficult problems at the crossroad where new mathematics, new physics, and the world's fastest computing intersected. Such grand challenge problems could only be solved on supercomputers if and only if the number of processors harnessed is sufficiently large. What's the importance of supercomputers to Nigeria? A Nigeria without supercomputing is a Nigeria with reduced petroleum revenue. In retrospect, the world's fastest computer suffered from the cost of rising expectations. The unorthodox supercomputer of 1989 that had only myself as its only full-time programmer reset itself to become the conventional user-friendly supercomputer that now has 1,000 simultaneous users. The grand challenge problem of supercomputing is a tough question that the petroleum industry must answer. Their answer must lift the common citizen in Nigeria from poverty. The answer must be grounded several miles deep inside the oil fields of the Niger Delta region of southern Nigeria. That oil field covers the area the size of a town. In Nigeria, extreme-scale petroleum reservoir simulators are used to discover and recover otherwise elusive crude oil and natural gas. On the 4th of July, 1989, I became the first person to understand how to solve a grand challenge problem and how to solve it across a new ensemble of processors that surrounded a globe as a new internet, that's a new global network of processors. That was how I became the first person to figure out how to solve the grand challenge problem of supercomputing and how to solve it across a never-before visualized internet that's a new spherical island of 1 binary million or 1 binary billion off-the-shelf processors that were coupled and which were equal distances apart and that shared nothing. The difference between each of the 25,000 vector supercomputer scientists of the 1970s and 80s and myself was this: I had the self-confidence to tackle the most difficult mathematical problems in supercomputing and to solve those once impossible problems alone, but only aided by my ensemble of 65,536 processors that computed in tandem. I visualized my new internet as encircling a globe in the manner the internet encircles the earth. In 1989, I was in the news as the mathematician that harnessed the first supercomputer as it's known today to solve such difficult problems. I solved them when every mathematician said that their mathematical solutions were impossible, even across an ensemble of 1 billion processors. At all times, and for the grand challenge problems, I was cognizant of the fact that calculus and algebra were the 2 recurring decimals on my blackboard and motherboard, respectively. Prior to the parallel processing of my computational fluid dynamics problem, I had to discretize a system of governing partial differential equations of calculus called the primitive equations of weather forecasting. That was how I invented my finite difference algorithms of the algebra of weather forecasting. Those algorithms are the sets of computational steps or the floating point arithmetic operations that must be solved at the extreme scale algebraic core of the compute-intensive problem at the core of weather forecasting. That was how your evening weather forecast used the second law of motion of physics to predict the motions of atmospheric flows and compute dependent variables and present them as sequences of contoured fields. The remaining equations used in weather forecasting include the hypsometric equation that was derived from the hydrostatic equation and the ideal gas law. It also includes the thermodynamic energy equation, or the first law of thermodynamics, that states that the change in internal energy is equal to the heat added minus the work done, and the continuity equation. Often, the mathematical formulation of the primitive equations of weather forecasting yields a system of 5 equations with 5 dependent variables that include the fluid velocity relative to the rotating earth, the density, and the pressure. A supercomputer that sells for $1 billion is more complex than a novel that sells for $20. My contributions to science cannot be published in science journals that has page limits. Nor can it be explained as a short-term memo to the White House. A memo can only convey a vague but not fully formed idea. The supercomputer or internet cannot be described within 6 pages or 1-hour lecture. For that reason, I described my contributions to the world's fastest computing. I did so across a series of 1,000 podcasts and YouTube videos. Writing my life story and contributions to the world's fastest computing, and doing so without dwelling on the 9 partial differential equations that I invented in the early 1980s, and while in College Park, Maryland, would be like producing the play Hamlet without the Prince of Denmark. I invented 9 new partial differential equations for mathematical and computational physics that are called the 9 Philip Emeagwali equations. The partial differential equation is the pinnacle of mathematical physics. The supercomputer is to the partial differential equation what the telescope is to astronomy. The new partial differential equations that I invented and that I figured out how to solve across the new internet that I invented was the cover story of top mathematics publications. Those publications include the May 1990 issue of the Siam News, published by the Society for Industrial and Applied Mathematics. My new partial differential equations made the news headlines because the new parallel processed mathematical computations which I executed across my new internet, that was a new global network of 65,536 processors, were science fiction to the community of research computational mathematicians of 1989. My contributions to mathematical knowledge were newsworthy because it was then impossible to parallel process and to solve at the fastest computer speeds the partial differential equations of extreme scale mathematical physics. The 9 partial differential equations which I invented were credited to me because they had never been scribbled across any blackboard or printed in any textbook or written in any known notebook. Because I invented those 9 partial differential equations, I knew them forward and backward and even sideways. For that reason, I delivered my mathematical lectures of the 1980s and now in prose and without notes or blackboards. Across YouTube, I'm the only mathematician that delivered his partial differential equations without PowerPoints. It was noted in YouTube commentaries that I was the only mathematician who delivered his mathematical lectures to leading mathematicians and delivered them in prose and poetry, and delivered original partial differential equations without notes. I delivered my new partial differential equations without notes, and I did so when other research computational mathematicians buried their faces on their blackboards, scribbled with partial differential equations and scribbled with companion partial difference equations, all borrowed from textbooks. Before February 1, 1922, theorized parallel processing existed as a blank sheet of paper or as science fiction. Before July 4, 1989, the parallel process solutions of the most compute-intensive problems only existed as science fiction. To discover that the fastest computer can be built with the slowest processors was news headlines because the invention shook the world of supercomputers. Before my experiment of July 4, 1989, that made the news headlines, the evidence that supported the technique and technology of parallel supercomputing was thin to non-existent. As a supercomputer scientist, my research quest was to invent the world's fastest computer and to invent how to compute across processors and compress times to solution of initial boundary value problems that arise when solving the most compute-intensive problems, such as global climate modeling to foresee long-term global warming. In 1989, I was in the news because I discovered how to compress the times to solution that was needed to solve the most compute-intensive problems in science, engineering, and medicine. My contributions to the development of the computer were these. I discovered how to compress the time needed to solve the most compute-intensive problems that were once impossible to solve, and how to solve them by sending and receiving emails and communicating along my new global network of 1,048,576 email wires. My initial boundary value problems of mathematical and computational physics were sent to and received from an ensemble of 65,536 coupled processors, in which each processor operated its operating system and shared nothing between nearest neighboring processors. Parallel processing creates more eureka moments, such as in the world's fastest computer that harnesses 10.65 million off-the-shelf processors and uses those processors to solve the most compute-intensive problems. Within the world's fastest computer, parallel processing is the vital technology used to reduce the time to solution from 30,000 years or 10.65 million days of sequential processing on one central processing unit to merely 1 day of supercomputing across 10.65 million central processing units. In one form of the primitive equations, or the system of hyperbolic partial differential equations that governs the difficult mathematical problem of extreme scale weather forecasting, the dependent variables are the zonal velocity in the east to west direction that is tangent to the sphere, the meridional velocity in the north to south direction that is tangent to the sphere, the vertical velocity in isobaric coordinates, the precipitable water, the Exner function or non-dimensionalized pressure, the potential temperature, the gas constant, the pressure, the specific heat on a constant pressure surface, the heat flow per unit time per unit mass, the temperature, the geopotential, and the time for the Coriolis force. What separated the serial and the parallel paradigms of the world's fastest computing is not the difficulty of the problems they solved, but how they solved it. Your weather forecast was enabled by the parallel processed initial boundary value problem based on the primitive equations of meteorology. Each equation was a balanced equation that accounted for something, such as where fluids come from or go to, and how the total fluid changes in time and space. The first of the 6 primitive equations encode the law of conservation of mass. The second, third, and fourth partial differential equation of the primitive equations encodes the law of conservation of momentum. The fifth partial differential equation of the primitive equations expresses the relationship between the temperature to heat sources and sinks. The general circulation model is a climate model based on the general circulation of the Earth's atmosphere and oceans. The climate model is an ensemble of millions of parallel processed initial boundary value problems of calculus, each governed by the primitive equations of meteorology. This system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations encoded some laws of physics and chemistry. To parallel process the global climate model, the supercomputer scientist must chop up the extreme scale mathematical problem into millions of smaller three-dimensional models. Each small global climate model computes in tandem the wind speed, heat transfer, relative humidity, radiation, and surface hydrology within itself. And it must exchange boundary value data with the nearest neighboring global climate models that were executed within the as many processors. I discovered how to slice and dice grand challenge initial boundary value mathematical problems and massively parallel computing them in smaller chunks and aggregating them for the complete results. My discovery of the world's fastest computing across the world's slowest processors made the news headlines because it was a big step towards the invention of super-fast computers computing at the speed limit. The world's fastest computer costs 40% more than the mile-long Second Niger Bridge of Nigeria. Why are supercomputers important in climate modeling? The world's fastest computer is used for the most detailed mathematical calculations, such as predicting long-term global warming. What is a world without supercomputers? The world's fastest computer is used to solve problems that did not exist before. The world's fastest computer costs $1.25 billion, or the equivalent of 25,000 man-years, with each man paid $50,000 per year. For this reason, a full-time computer science instructor that conducts part-time research aided by only 3 20-year-old students cannot construct the world's fastest computer. A state-of-the-art computer is 1 billion times more powerful than the everyday computer. The fastest computer in the world is far more complex than the spacecraft that took men to the moon. The development of the most powerful computer demands up to 25,000 pairs of hands and as many brains. On the 4th of July 1989, I recorded the highest speed up and the fastest speed in supercomputing. That scientific discovery led to my conclusion that supercomputing across the slowest 1 billion processors could become the technology that can yield a factor of 1 billion-fold reduction in the wall clock times of the most compute-intensive problems. Such grand challenge problems include global climate models that must be used to foresee otherwise unforeseeable long-term global warming. Without parallel supercomputing, it would take centuries to foresee climatic changes. What is the difference between the global climate model and the general circulation model? The general circulation model simulates the circulation of the atmosphere. A global climate model might be based on a general circulation model. The global climate model is used to predict what will happen in the Earth's climate in the coming centuries. The climate in London is the average weather in London for over 30 years. My mathematical contributions to the solution of the primitive equations used to forecast your evening weather were these. I discovered how to parallel process and compress the time needed to solve the grand challenge problem of weather forecasting that is an extreme scale initial boundary value problem of computational physics. I discovered that with 10.65 million processes computing in parallel, that a time to solution of 10.65 million days or 30,000 years dropped to 1 day of time to solution across a new internet that's a new spherical island of 10 binary million processors. Without parallel supercomputing, tomorrow's weather forecast will be issued 30,000 years later. A famous debate on the future of the parallel supercomputer took place between April 18 to 20, 1967, and at the Spring Joint Computer Conference in Atlantic City, New Jersey. After that debate, the consensus was that parallel supercomputing will forever remain an enormous waste of everybody's time. That debate was between IBM's Gene Amdahl, who opposed parallel supercomputing, and Daniel Slotnick, who proposed parallel supercomputing. Gene Amdahl, who designed the world's most successful single-processor computer, named IBM's System 360, won that debate, and his victory gave rise to the famed Amdahl's law that later entered into supercomputer textbooks. Amdahl's law decreed that it would be wasteful to design supercomputers that are powered by 8 or more processors. According to Amdahl's law, an infinite number of processors will be wasteful and will not yield an infinite increase in the speed of the parallel supercomputer. Amdahl's law was the reason fewer than 8 processors were incorporated into the supercomputers of the 1960s through 80s. On July 4, 1989, I discovered the new supercomputing knowledge of the world's fastest computing across the world's slowest processors. That contribution is the reason I'm the subject of school essays on computer history. On my blackboard, I use the most advanced expressions from the frontier of calculus and computational fluid dynamics. Those expressions are called partial differential equations. Partial differential equations are used to foresee the motions arising during plate tectonic, supernovas, and tornadoes. Partial differential equations are used to design superconducting magnets for superconducting supercolliders. Partial differential equations are used to design superconducting magnets for supercolliders. Partial differential equations are used to foresee the motions arising during plate tectonic, supernovas, and tornadoes. Partial differential equations are used to study the transport of ions across kidney membranes. An ion is an atom or molecule with a net electric charge arising from the loss or gain of electrons. But by far, the most important and the most frequently occurring partial differential equations are those that encode laws of physics, such as the conservation laws for matter, momentum, and energy, and chemical species. The laws of conservation are the common denominators in many initial boundary value problems, such as those arising in extreme scaled parallelized computational fluid dynamics, such as modeling the hurricanes and tornadoes to protect life and property, and the design of hypersonic aircraft, quiet submarines, and efficient automobile bodies. In the fluid dynamics of the Earth, the solutions of the governing partial differential equations are the mathematical descriptions of both the oceanic and the atmospheric flow patterns. That mathematical and computational solution is simply called short-term weather forecast, or the long-term global warming prediction. The formal mathematical name for this is initial boundary value problem. It's a boundary value problem because the Earth's surface is its lower boundary, while the Earth's upper atmosphere, that is 62 miles or 100 kilometers above the Earth's surface, is its upper boundary. The world's fastest computing is the key technology that must be used to address the grave existential threats of the 21st century. The biggest threat to life on Earth is to understand the abstract and seemingly invincible global climate change. We lack the visceral understanding of the urgency of global warming. In the long run, the proximity of the climate crisis is worse than any global pandemic and economic collapse we can imagine. Parallel supercomputing that was once confined to solving compute-intensive initial boundary value problems is now used to solve mathematical problems that arise across many industries. The world's fastest computers are used to foresee long-term global warming, reduce the energy crisis of the world, search for extraterrestrial intelligence, understand how living cells function, mark the human genome, kill diseases, and speed up the search for new antiviral drugs and for new vaccines with the least side effects. I invented the blueprint that's used to design the first supercomputer as it's known today and as it could be known tomorrow. My discovery, which occurred on July 4, 1989, opened the door to the world's fastest computers that compute across an ensemble of up to 1 billion processors. What happened in 1989 was that I invented something that was waiting for me. My contribution to the development of the computer is this. I was in the news for discovering that the world's fastest computers can be manufactured from standard parts known as off-the-shelf processors, including from the world's slowest processors. My supercomputer invention made the news headlines because it provided the answer to the most pressing question at the crossroad where mathematics, physics, and computing intersected. After my discovery, it became possible to simulate long-term global warming. I do so faster and across up to 1 billion processors. Today, the world's fastest computers are powered by up to 10 million processors. The reason is that 10 million processors powering a supercomputer makes it possible to obtain a more detailed and realistic global climate models that must be used to foresee century-long climate changes. Why is the fastest computing across the slowest processors a critical and enabling technology? And what is the contribution of Philip Emeagwali? My contribution to the development of the computer is this. I discovered how to populate the world's fastest computers with 1 billion processors that shared nothing but were in dialogue with each other. And I discovered how to solve the hardest problems and solve them by chopping them up into 1 billion smaller problems that can then be solved in tandem. I discovered that rapid fire speed, that's the first world's fastest computing to be executed across the world's slowest processors, and discovered it as modular. Therefore, the supercomputing technology can be repeated 1 billion-fold to gain as much speed increase. In a different perspective, if all our high-resolution, three-dimensional, and time-dependent computational fluid dynamic simulations, we are represented by one uninterrupted simulation that's executed within one processor, then our pre-human ancestors who used the first stone tools may have had to start our supercomputing simulation and started it 3 million years ago so that we can have their answer today. That technological feat called for a civilization on Earth that pre-existed before humans. The supercomputer that is powered by millions of processors is the lifeblood of science, engineering, and medicine. Yet the world's fastest computers are taken for granted and undervalued. In 1989, I was in the news for discovering that the slowest processors could be used to solve the biggest problems and find their answers at the fastest speeds. The fastest computer is why you know the weather before going outside. Shortly after 1989, a 12-year-old writing an essay asked me, "Are you a black genius?" The genius is the ordinary person that found the extraordinary in the ordinary. My father is a genius because he insisted that I solve 100 mathematics problems every evening and solve them faster than one problem per minute. At that speed, I was one of the fastest human computers in Nigeria, and that daily exercise foreshadowed my world's fastest computing of July 4, 1989. In 1989, I was in the news for discovering how to solve the most compute-intensive problems at the intersection of calculus, algebra, physics, and computing. I was in the news for discovering how to solve the most compute-intensive problems and solve them at the fastest recorded computer speeds and solve them with the slowest processors in the world. In 1960, in Sapele, Nigeria, British West Africa, I came last in my first grade examinations and last in mathematics. I dreaded mathematics, but my father demanded that I study 20 times longer than my classmates. After 5 years of daily practice, in the late weekday afternoons, I was solving 100 arithmetical problems an hour. In comparison, my primary school classmates were solving only 5 problems each school morning. I studied 20 times harder to become only twice better. The genius is the below average person that worked hard to become above average. It's a myth that only persons possessing the highest IQs can contribute new knowledge to science. Brilliance is a necessary condition for inventing faster computers and for solving unsolved problems at the frontiers of mathematical knowledge. But brilliance, in and of itself, is not a sufficient condition for experimentally discovering how millions of the world's slowest processors could be harnessed and used to execute the world's fastest computing and solve the hardest problems in mathematics. I was in the news because I discovered that solving up to 1 billion problems at once enables supercomputers to be up to 1 billion times faster than computers. That's how I invented the technology that enables the world's fastest computers to be fastest. It's one thing to have exclusive control of 65,536 processors that could make a supercomputer fastest. It's another thing to visualize those ensembles of processors as a new internet. It's another thing to envision routing emails across a new internet defined and outlined by one binary million or 1,048,576 bidirectional email wires that were regular and short and equal distances apart. It's another thing to understand how those email wires married those processors together and married them as one seamless, coherent, and gigantic processor. The world's most powerful supercomputer is like a wristwatch. You only see the face and the hands of a wristwatch. The unseen inside of the wristwatch is abstract but necessary. My unseen ensemble of 65,536 processors were like the inside of the wristwatch that is abstract but necessary. My ensemble of 65,536 processors that shared nothing didn't solve the as many compute-intensive problems of computational physics and didn't solve them by themselves. A central processing unit is like a coffin that's merely a box until you put somebody inside it. I used those 1,048,576 regular, short, and equidistant email wires to send emails to and from processors, and I used them to deliver the most compute-intensive problems of mathematical physics that I subdivided into 65,536 smaller, less compute-intensive problems, and to deliver their companion instructions on how to solve those smaller problems, and to deliver the smaller problems with a one-problem-to-one processor correspondence, and do so to all 65,536 central processing units that outline my new internet. That's a supercomputer in reality. That ensemble of 64 binary thousand processors was my laboratory instrument that made it possible for me to discover how parallel processing enables computers to be faster, and discover why the new technology enables the world's fastest computers to be fastest. What did Philip Emeagwali contribute to the development of the computer? The processor is the brain of your computer. My contribution is like having 1,000 brains in your computer. My invention is like powering the world's fastest computer with 1 billion brains. As the inventor of the Philip Emeagwali computer, I had to know a priori the topology or the locations of each processor within my ensemble of processors. I know where every processor or electronic brain is located, and know those locations both forward and backward, and know them with the completeness an airline pilot had to know the geography of Nigeria to fly from Lagos to Abuja. I visualize short email wires for processor-to-processor email communications. I visualize them as comprising of email wires printed onto circuit boards. I visualize long email wires that comprised of fiber optic cables or electric cables. Furthermore, I visualize my ensemble of processors as communicating and computing together and doing both as one seamless, coherent, and giant processor that's the world's fastest. Not only that, I visualize using commodity or large numbers of available processors designed for computers. That was in contrast to using a few custom-made vector processors that were designed for the fastest supercomputers of the 1970s and 80s. My contribution to computer science is that I made the unimaginable possible And I did so when I discovered how to encode the laws of physics into the partial differential equations of calculus that I discretized into systems of equations of algebra that I coded and solved across a new internet. I invented my new internet as a new global network of coupled 65,536 central processing units that shared nothing. In supercomputing, to discover or invent is to show that the impossible to solve is possible to solve. And to apply that new knowledge, that new supercomputer knowledge, to get answers to previously unanswerable questions, and thus discover the extraordinary in the ordinary. The genius is the ordinary person that found the extraordinary in the ordinary. I executed the world's fastest computing to know what's discoverable and knowable, and know something which nobody knows. To witness a scientific discovery that has rich, fertile, and far-reaching consequences is like walking into a forest and witnessing many leaves fall on your head. Leading mathematicians first learned about Philip Emeagwali were my contributions to extreme-scale computational linear algebra, arising from the discretizations of the partial differential equations of calculus. My contributions to large-scale computational physics became the front-page story of the May 1990 issue of the Science News. The Science News is where new contributions to mathematical knowledge are described by mathematicians and for mathematicians. As a black mathematician born in colonial Africa, I was compelled to invent new mathematics while conducting research alone. I'm different from modern mathematicians of European ancestry. I'm different because I performed my arithmetic computations in parallel or multiply 65,536 pairs of numbers at once. I'm different because modern mathematicians perform their arithmetic computations and do so in sequence or multiply two numbers at a time. I'm different from the pure mathematician who uses the blackboard as his mathematical canvas. I'm different because I'm a large-scale computational mathematician who abandoned his blackboard and embraced a new internet that he invented as a new global network of 64 binary thousand processors that each had its dedicated memory. I embraced up to 1 billion processors as my mathematical canvases. I'm different from the applied mathematician that applies a real-world mathematical problem, such as global climate model that must be used to foresee global warming. I applied the global climate model as my backdrop for my global network of processors. I'm different because I applied both the mathematics and the problem as the backdrops to the new internet I invented as a new global network of 64 binary thousand central processing units. I'm different from the computational mathematician who only uses the motherboard as his mathematical canvas. I'm different because I used a new internet that's not a computer by itself. I used the world's fastest computer as my new mathematical canvas. What is the contribution of Philip Emeagwali to mathematics? I changed the way mathematicians solve the most difficult problems arising in mathematics, physics, and computer science. In my new way, the hardest problems are solved across up to 1 billion processors instead of within only one processor. That was a paradigm shift. The lyrics of a song are sung, not read. If the lyric is meant for the microphone, not the page, then the largest scale system of equations of algebra is meant for the motherboard, not the blackboard. Programming across an ensemble of processors demands message passing or sending and receiving emails from processor to processor. My processor to processor email instructions are to me is parallel programmer what the play is to the Shakespearean actor. Like the play, my communication primitives were acted upon, not read. Large-scale algebra is the recurring decimal in large-scale computational physics. I used the largest systems of equations of algebra that define the toughest problems in computational physics and engineering as my backdrops or as my supercomputer testbed grand challenge problems. I challenged the established truth. That established truth of the 1980s and earlier was that the slowest central processing units can't work together to solve the most compute-intensive problems in algebra, or can work together to solve the most compute-intensive problems in algebra or in large-scale computational physics and engineering. The contributions of Philip Emeagwali to mathematics were these. I changed the way we solve compute-intensive mathematical problems. In the bygone way, mathematicians computed on merely one isolated central processing unit that wasn't a member of an ensemble of processors, or within merely one isolated computer that wasn't a member of an ensemble of computers. In my modern way, mathematicians compute across millions of central processing units or across millions of processors. What is the Philip Emeagwali Internet? The eureka moment or high point of my quest for the fastest computer in the world occurred at 15 minutes after 8 o'clock in the morning of July 4, 1989 in Los Alamos, New Mexico, USA. And it occurred inside my ensemble of the slowest 65,536 processors in the world. I invented a new internet that was made up of 64 binary thousand processors, or equivalently 65,536 computers that were uniformly distributed across the surface of a globe. That new global network of 65,536 processors was my small copy of the internet that's also a global network of computers. What is the Philip Emeagwali Internet? Any global network of processors or computers that uniformly encircles a globe in any dimension is called the Philip Emeagwali Internet. I'm the only father of the internet that invented an internet. In the 1980s, my processors communicated via emails that contained 65,536 computational fluid dynamics codes that I sent from up to 16 nearest neighboring processors. My computer codes and email primitives were esoteric and weren't meant to be read by humans. I was in the news because I discovered how to harness millions of the slowest processors in the world and harness them as one seamless, coherent, gigantic unit that's the world's fastest computer in reality. In computer science, the most coveted achievement bar none is to discover how to record once unrecorded speeds in computations and to apply that knowledge to solve the most compute-intensive problems in science, engineering, and medicine. In the 1970s and 80s, parallel processing, or computing many things at once, instead of computing only one thing at a time, was dismissed as a beautiful theory that lacked an experimental confirmation. In 1979, parallel supercomputing stood on a shaky ground. In 1980, I was dismissed from my research team because I advocated that the world's fastest computing can be achieved from harnessing the world's slowest processors. At that time, I was seen as a mathematician and a physicist and an outsider to computer science. For those reasons, they did not want me to publish and speak about parallel processing. I was deplatformed and remained voiceless until July 4, 1989. In a syndicated article distributed on September 2, 1985, and distributed to the print media, and distributed by the United Press International, or UPI, and in that article, John Rollwegen, the president of Cray Research Incorporated, the company that manufactured 7 intense supercomputers, described their use of 64 processors as, quote-unquote, more than we bargained for. In the November 29, 1989 issue of the New York Times, Neil Davenport, the president of Cray Computer Corporation, the sister company to the company that manufactured 7 intense supercomputers, warned that we can't find any real progress in harnessing the power of thousands of processors, unquote. The fastest computer is 1 million times faster than your computer. The fastest computer is the heavyweight champion of the computer world. After my scientific discovery of how to record the fastest computer speeds and record them across the slowest processors in the world, the technology of parallel processing was reclassified from an unconfirmed theory to reality. Prior to my discovery that occurred on July 4, 1989, the supercomputer as it's known today was not a computer, and its market was virtually non-existent. Parallel supercomputing that was once the stone widely rejected as rough and unsightly entered computer science textbooks and did so after my discovery, which occurred on July 4, 1989 in Los Alamos, New Mexico, USA. Parallel processing could power future quantum computers. Parallel supercomputing changed our understanding of the fastest computer in the world and made it possible for me to harness a new internet as my new global network of processors and as my new supercomputer de facto. For the decade of the 1980s, I sat alone staring at an abandoned computing machinery that everybody else ridiculed and abandoned as a tremendous waste of everybody's time. There was no instruction manual on how to harness the power of the then never before seen supercomputer hopeful that was abandoned for me to program alone. Nor was there a help desk that could explain how I could synchronously send and receive 64 binary thousand emails. I discovered how to solve the most compute-intensive problems and solve them across each of those central processing units and solve them with 16 orders of magnitude increase in supercomputer speed. I visualized my computer codes and their arithmetic data as transmitted via emails and sent and received along 16 directions that were in a mathematical sense mutually orthogonal. Those 16 directions that are perpendicular, mutually perpendicular in an imaginary 16-dimensional hyperspace. I discovered how to compress 65,536 days or 108 years of time to solution on a computer and compress that time to solution to 1 day of time to solution on a supercomputer and compress that time to solution by 16 orders of magnitude. My scientific discovery of 108 years in 1 day opened the door to the state-of-the-art supercomputing of compressing 30,000 computing years on an isolated processor to 1 supercomputing day across an ensemble of 10.65 million processors. I discovered how to compress 30,000 years to 1 day. It's the parallel processing that I discovered on July 4, 1989 that powers the 1,000 fastest computers in the world. The fastest computer is powered by up to 10.65 million central processing units and used to solve the most compute-intensive problems and solve them in parallel. My scientific discovery opened the door to supercomputing a million or even a billion things at once. My discovery of the fastest computing across the slowest processors is permanently embodied inside every supercomputer. The fastest computing enables us to get a surer and deeper understanding of our universe and enables us to foresee otherwise unforeseeable long-term global warming. The fastest computing enables mathematicians to climb higher up the ladder of scientific knowledge. To the computer scientist, it made the unimaginable to compute possible to supercompute. My contributions to mathematics, physics, and computing were that I discovered how to harness up to 1 billion processors and use them to solve the most complex calculus problems, such as the system of partial differential equations that governs the initial boundary value problems of the most extreme-scaled computational fluid dynamics. The world's fastest computer was used by computational physicists to model once-in-a-century global pandemics and simulate the spread of contagious viruses. The world's biggest computer, that occupies the footprint of a football field, was used to attack COVID-19 from multiple angles. I'm here because I discovered the new knowledge that enables your computer to be faster and enables the world's fastest computer to be fastest. I was in the news because I discovered the world's fastest computing across the world's slowest processors. I discovered how to use that new supercomputer to solve the world's most difficult problems, such as executing the core mathematical calculations that arise when investigating the cure and spread of COVID-19. I discovered how the fastest computers can be used to pinpoint the locations of crude oil and natural gas that are buried up to 7.7 miles deep. Before my discovery of parallel supercomputing, only one giant vector processor, or maybe 4 or 8 superfast vector processors were used to power the fastest computers. After my discovery of supercomputing as it's known today, millions of off-the-shelf processors were used to tackle the most difficult problems arising in science, engineering, and medicine. The scientific discovery is the nothingness from which new knowledge sprang. That new knowledge makes the discoverer a messenger from God. My goal wasn't to perform the fastest computation and the fastest communication in itself. My goal wasn't to solve my partial differential equations per se and solve them to the 17th decimal place. My goal was to see the plural as the singular. My goal was to see 65,536 central processing units as sharing nothing but coupled, and to see them as one coherent, seamless supercomputer that's 65,536 times faster than one computer, computing with only one giant processor. My goal was to see a 16-network deep internet and see it as a small copy of the internet of the future. I invented the form of a new supercomputer that's a new internet or a new global network of processors. My new supercomputer is my metaphor for my new internet. My invention was an internet in form, but a supercomputer in function that's encoded across its millions of off-the-shelf processors that shared nothing. My invention opened the door to the manufacturing of supercomputers out of standard parts, such as off-the-shelf processors. After my discovery that occurred on July 4, 1989 in Los Alamos, New Mexico, USA, each of the world's fastest computers was powered by an ensemble of millions of separate processors that operated in tandem with each other. Back in 1990, I declined the invitation to help the US simulate nuclear explosions and do so on the world's fastest computers. My discovery that the world's fastest computers can be manufactured from millions of off-the-shelf processors made it possible for nuclear weapons to be tested by simulation on the supercomputer that's powered by millions of processors. My discovery rendered physical testing obsolete. That's the reason nuclear explosions are simulated across millions of coupled processors. It's now obsolete to test nuclear bombs at test sites in the South Atlantic Ocean and off the coast of Southern Africa. I was searching for the universal in the particular. I was searching for the extraordinary division in the ordinary multiplication. I was searching for the extraordinarily fast addition in the ordinarily slow subtraction. I was searching for the extraordinarily deep 16-dimensional hyperspace for the ordinary one binary million zeros and ones that define the total 16-bit long addresses of my 2 raised to power 16 ordinary central processing units that outlined a new internet that's de facto a new supercomputer. In a century, the supercomputer could be the size of the Earth, and it will look like the internet and be parallel processing across the internet. In year million, what will posthumans look like? In 1 million years, our posthuman gods will not look like us. Our super intelligent posthuman gods could cross a scientific frontier of knowledge that will be science fiction to us. I foresee our descendants of 1,000 millennia to be super intelligent lizards that could be masquerading as post-human gods in their overpopulated planet Mars. I foresee an Earth-sized brain that is anthropomorphized and thinks like a super intelligent being. I foresee a neural super brain for our post-human gods of year million. I foresee trillions upon trillions of super brains of year million colonizing our Milky Way. I foresee intergalactic space travelers in year million. The supercomputer will be the walking stick in humanity's million-year hero's journey to the primal place of immortality. That scientific journey to envision our post-human gods could be akin to visiting the planet of the cyborgs, where each cyborg is half human and half super intelligent computer. That journey to envision post-human cyborgs will be akin to in a spiritual sense, visiting the lands of the spirits of my distant Igbo ancestors. By year million, our post-human gods could reinvent themselves as asexual cyborgs. I foresee that each cyborg of year million could be half human, half computer. I foresee that each cyborg of year million could have a sixth sense of humor. I foresee that each cyborg of year million could be a disembodied brain floating in the middle and safety of the Atlantic Ocean. Our cyborg posthuman gods of year million could be anthropomorphic or have human attributes. Our cyborg posthuman gods of year million could be human-like because we humans will create them in our own human image. Our cyborg posthuman gods will not have computers around them or have their internets around their planets. The computer of year million could be within them. They may not need computers because in year million, because there could be computers. I'm here because I discovered how parallel processing enables computers to be faster and why the technology enables the world's fastest computers to be fastest. The discovery is a time machine that takes us to the past and enables us to see a thing that pre-existed but yet remained unseen to our ancestors. The invention enables us to invent the future of our descendants. The parallel supercomputer, once the stone rejected as rough and unsightly, is now the headstone of the computing industry. Parallel computing, or solving many problems at once or in parallel, instead of solving one problem at a time, is what makes nearly every computer faster and makes every supercomputer fastest. My scientific discovery of fastest computing made the news headlines in 1989 and opened the door to large-scale computations in mathematics and physics. I foresee our children's children opening more doors by fastest computing across their internet that will be their spherical island of trillions of central processing units that enshroud the Earth. And do so as their planetary supercomputer. Such speed of light fast supercomputers could solve our as yet unsolved compute intensive problems. 1 million years ago, our human ancestors looked like apes. in 1 million years or in a million, our human descendants will ridicule us as looking like humans. In 1 million years, we might have only living silicon as our posthuman gods. In 1 million years, our posthuman could live forever. In a billion, the aliens on Earth could be us. I envision posthumans as thinking across a 10,000-mile diameter cosmic superbrain that will sprawl across an epic landscape of their 8 continents that will be hanging on the cloud and that will enshroud our 7 land continents and enshroud the Earth with their million electronic cloth. I foresee posthumans to be half humans and half thinking machines. The grandchildren of our grandchildren will not use their internet the way we use our internet. Their internet could be within them while our internet is around us. They may not need supercomputers because their computers could be within them. Large-scale computational fluid dynamics is a direct extension of classical physics and modern calculus. It's an extension of the first world's fastest computing across the world's slowest processors. I was in the news because I discovered that fastest computing at 8:15 in the morning on July 4, 1989. Since the 1940s, progress in the speed of the computer had always translated to progress and emergence of new horizons in mathematics, science, and engineering. The poster child of the 20 grand challenge problems classified by the US government is the extreme-scaled computational fluid dynamics codes used to simulate the spread of a once-in-a-century global pandemic. The supercomputer must be used to correctly and accurately simulate the spread of virus droplets among the billions upon billions of train passengers around the world that are packed like sardines. The supercomputer is used to simulate ways of stopping the spread of contagious viruses, or to simulate the spread of a once-in-a-century global pandemic's contagious viruses across the 2.5 billion passengers a year that rides in Russia's Moscow metro. A world of magic and science resides inside the bowels of the world's fastest computer that occupies the footprint of a football field. And it costs 40% more than the mile-long Niger Bridge in Nigeria. Please allow me to reintroduce myself. My history began on August 23, 1954, my date of birth in the servants' quarters at 11 Ekemeso Street, Akure, Nigeria. At age 19, I was in Corvallis, Oregon, USA, programming a supercomputer that was the first to be rated at 1 million instructions per second. I was supercomputing in Los Alamos, New Mexico, USA by July 4, 1989, and at the world's fastest speeds. In 1949, and 5 years before I was born, my parents, who were born in Onitsha, had independently migrated from Onitsha to Kano, which was then 600 miles away. They both lived in the strangers' quarters of Kano, called Sabongari in the Hausa language. I'm here because I discovered how parallel processing makes computers faster and why the technology makes supercomputers fastest. My discovery is called parallel supercomputing. The supercomputer impacts today and enables us to imagine tomorrow. Fast computation defines the computer. The fastest computation is the only objective milestone and measurable contribution to computer science. Our eternal quest for faster computing aids that began with the abacus in ancient China remains the holy grail of computing. My technological quest had one fundamental change. It was of tectonic scale. It was called parallel supercomputing, or solving millions of mathematical problems at once instead of solving only one problem at a time. Parallel processing is the enabling technological knowledge that enabled your computer to be faster and enabled the world's fastest computer to be fastest. 9 out of 10 supercomputer cycles are consumed by large-scale computational physicists alone. Within the world's fastest computer is a world of magic in which the physicists can foresee otherwise unforeseeable natural events. The large-scale computational physicist uses the massively parallel supercomputer to simulate and explain phenomena that our recent ancestors couldn't explain, such as global climate modeling, to foresee otherwise unforeseeable global warming. I was in the news because I discovered how to use millions of processors that shared nothing to solve the most compute-intensive initial boundary value problems in mathematical physics, including problems arising from encoding the laws of physics into a system of partial differential equations of calculus. I also discovered how to reduce such systems of partial differential equations and reduce them to a large-scale system of equations of computational linear algebra that approximated them. I also discovered how to reduce such systems from algebra to a set of mathematical calculations that approximated them. Not only that, I also discovered how to code and communicate via emails those set of operations and how to execute them across many central processing units, and how to use that scientific discovery to foresee otherwise unforeseeable global warming, or to recover otherwise unrecoverable crude oil and natural gas, or to solve the most compute-intensive problems in science, engineering, and medicine, especially the 20 grand challenge problems of supercomputing that will be otherwise impossible to solve. 1 in 10 supercomputers are used across the 65,000 oil fields of the world and used to process data at the highest resolution. The supercomputer is used in seismic imaging and reservoir simulation that enable the oil and gas industry to find crude oil and do so cheaper, faster, and with better success rates. The supercomputer is the petroleum geologist's best friend. The reason my scientific discovery of fastest computing was cover stories in 1989 was that it was a discovery that opened a promising line of research into computational science and computer architecture. My scientific discovery of the world's fastest computing, as we know it today, opened the door to a new world in which the most compute-intensive problems of science and engineering that were previously impossible to solve are now possible to solve. My scientific discovery of the world's fastest computing opened the door to the new world of computing across up to 1 billion processors that are coupled. In my new paradigm, the computational physicist can parallel process across an ensemble of up to 1 billion central processing units. Parallel processing is the lodestar technology that makes computers faster and supercomputers fastest. The reason my scientific discovery of how to compute faster and how to do so by changing the way we think about the supercomputer is a marker of progress is that it makes the impossible to solve possible to solve. The fastest supercomputer occupies the footprint of a football field. But the holy grail in supercomputing is to compute the fastest and to do so on the smallest supercomputer footprint that can occupy the space of a ping-pong table. Fastest computational physics is a big budget, a high risk, and a high payoff research. Executing the fastest and the largest scaled computational physics costs the budget of a small nation, but it pays off because it's the critical technology used to discover and recover otherwise elusive crude oil and natural gas buried up to 7.7 miles or 12.4 kilometers below the surface of the earth. Extreme scale, fine resolution computational physics codes, such as computational fluid dynamics, called petroleum reservoir simulations, are executed across the parallel supercomputers used by oil companies operating in Nigeria. Why are the fastest computers important? And what will the world be like without the supercomputer? The computer of today was the supercomputer of yesterday. A world without supercomputers may become a tomorrow without computers. To parallel process or to solve up to 1 billion problems at once instead of solving one problem at a time is fundamental knowledge that appears in up-to-date textbooks in computational physics. Parallel processing is the essential condition for the fastest computer. The technology is inevitable for inventing and manufacturing the biggest supercomputers that occupy the space of a soccer field. And it costs up to $1.25 billion each. Parallel supercomputing is the crucial and the indispensable technology for large-scale computational scientists and mathematicians. Without parallel processing, the world's fastest computer will take 30,000 years to solve a problem it now solves in only one day. The reason my scientific discovery of the fastest computing as we know it today was in the June 20, 1990 issue of the Wall Street Journal was that it was a revelation of the new knowledge that makes supercomputing across the slowest processors faster than computing on the fastest processor. Parallel supercomputing was the discovery that opened doors in large-scale computational physics. Supercomputing across the slowest processors was the discovery that opened doors for modeling in energy, aerospace, and automobile industries, as well as obtaining deep insights into existential issues like climate change and the spread of COVID-19. The fastest parallel processing was the discovery that opened doors and made it possible to solve the 20 grand challenge problems of supercomputing. Those compute-intensive problems were previously impossible to solve. In the 1980s, the technology of parallel processing that has permeated into every supercomputer of today was like a black box in a dark room. A discovery is like a light at the end of a dark tunnel. I'm Philip Emeagwali. I visualize my ensemble as 65,536 or 2 raised to power 16 equidistant points of light evenly distributed across the surface of a globe that I also visualized as embedded into a dark 16-dimensional universe. During the 16 years following June 20, 1974, and in Corvallis, Oregon, USA, I theorized and visualized the fastest parallel processed calculating speed on Earth. Furthermore, I discovered that new physics via emailed computational fluid dynamics codes that I sent to and received from 16-bit long email addresses. Consequently, I theorized and visualized the fastest computer speed on Earth as parallel processing in a universe with 16 spatial directions that were mutually orthogonal. The world's fastest computers are used to predict long-term weather, design safer cars, manufacture fuel-efficient airplanes, and develop new drugs. The high-performance computing industry relies on an ensemble of up to 1 billion processors to guide its most compute-intensive simulations. In the 1980s, I, Philip Emeagwali, was the only full-time programmer of the supercomputer Hopeful that was powered by the slowest 64 binary thousand processors in the world. I visualize my processors as outlining a small internet. For a large-scale computational physicist and supercomputer programmer Hopeful, who came of age in the decades of the 1970s and 80s, programming across that then unimagined new internet and programming its processors alone was a technological quest akin to a visceral journey to an unknown world. In the 1970s and 80s, parallel supercomputing was an unknown field of knowledge where it was hoped that the technology Hopeful will leave the realm of science fiction to become non-fiction. For me, Philip Emeagwali, supercomputing across the slowest processors was a 16-year-long visceral journey through the most abstract calculus, through the largest scale algebra, and through the most compute-intensive mathematical calculations in computational physics that I executed across supercomputers that I imagined as powered by up to 1 billion computers that surrounded a globe as a new internet. I, Philip Emeagwali, controlled and programmed each of my 64 binary thousand processors. I programmed them via emails that I sent to and from each of my as many 16-bit long email addresses. In the 1970s and 80s, supercomputer textbook authors wrote that to parallel process a large-scale computational physics code, such as global climate modeling, or to solve many problems at once, instead of solving one problem at a time, will forever remain an enormous waste of everybody's time. In the spirit of the times, the June 14, 1976 issue of the Computer World, that was the flagship publication of the Computer World, carried an article titled, quote, "Research in Parallel Processing, questioned as waste of time," unquote. What is the contribution of Philip Emeagwali to the development of the computer and the internet? Instead of using one giant processor as dictated by conventional wisdom, I visualize my one binary million 16 times 2 raised to power 16, or 1,048,576 bidirectional edges of the cube in the 16th dimension, as having a one edge to one email wire correspondence with the Philip Emeagwali internet, that is a global network of 64 binary thousand, or 2 raised to power 16, or 65,536 off-the-shelf processors that shared nothing. The following timeline and facts speak for themselves. In the 1950s and 60s, the top 1,000 supercomputers in the world performed their fastest when using merely one isolated scalar processor that wasn't a member of an ensemble of processors. By the 1970s and 80s, the top 1,000 supercomputers in the world performed their fastest by using merely one isolated vector processing unit that wasn't a member of an ensemble of vector processors. By the 1990s and later, the top 1,000 supercomputers in the world performed their fastest by harnessing the slowest 65,536 processors, or harnessing up to 10.65 million processors that work together to solve the most compute-intensive problems, such as global climate modeling. Those millions of processors communicate and compute together and do both as one seamless, coherent, and gigantic supercomputer. From those three timelines, the way we think about the computer and the supercomputer changed after my discovery of July 4, 1989. So, what happened in mid-1989 that convinced the world of computing to change the way it thought about the computer, change the way it thought about the supercomputer, and change its long-held opinion that parallel supercomputing will forever remain an enormous waste of everybody's time? My scientific discovery of the world's fastest computing happened at 8:15 in the morning of the 4th of July 1989. My discovery that parallel processing will make computers faster made the news headlines in 1989. My invention enables massively parallel computing and communicating across an ensemble of up to 1 billion processors to make supercomputers fastest. Since 1989, my invention has been the subject of millions of school essays. My discovery was mentioned in the June 20, 1990 issue of the Wall Street Journal. I discovered that we must look at the modern supercomputer as powered by off-the-shelf processors and standard parts. At that time, conventional supercomputers were powered by the fastest and custom-made central processing units. I discovered that the slowest 65,536 processors in the world could be harnessed and used to increase the speeds of computers and supercomputers. To discover the supercomputer of tomorrow that can solve up to 1 billion problems at once, instead of solving one problem at a time, is to see parallel supercomputing compress the time to solution of the toughest problems in large-scale computational physics and compress that time to solution by a factor of 1 billion. In 1989, it made the news headlines when I discovered how to compress the time to solution of the most compute-intensive problems in supercomputing and compress that time from 65,536 days or 108 years to merely 1 day across the world's slowest 65,536 processors. The scientific discovery of the world's fastest computing that I recorded from my email experiments of July 4, 1989, provided the designers of the first supercomputer that computes fastest across the slowest processors with the insight and the knowledge that massively parallel processing is the enabling technology to be used to compress the time to solution of the most compute-intensive problems and compress that time to solution from 30,000 years to merely 1 day. That supercomputer speed up from 1 day to 30,000 years was radical instead of incremental. Climate modeling is the most important problem in large-scale computational physics. Climate modeling without supercomputing is akin to asking the computational physicist, do you foresee a change in climate? And getting the answer 30,000 years later. The world's fastest computer should be taken to wherever the most difficult problems are. As a mathematician in search for the world's fastest computer that computes in a radically new way, my mandate was to push myself to the very edge of knowledge of computer science and to what could be computed and then continue beyond the world's fastest computer. No matter what the unsolved problem is, my goal was to change the course of history. My new knowledge of the world's fastest computing across the world's slowest processors changed the way we look at the supercomputer and changed the way mathematicians solve their most difficult problems. My scientific discovery of how to solve the most compute-intensive problems and solve them by chopping each problem up into up to 1 billion lesser challenging problems that can be solved across and at once up to 1 billion processors was multidisciplinary. My solution of that grand challenge problem spanned the frontiers of knowledge of geophysical fluid dynamics, partial differential equations, extreme scale algebra, and the world's fastest computing across millions of processors that encircled a globe as a new internet. Briefly, I encoded a set of laws of physics. I encoded those laws into calculus. I translated that calculus into algebra. I further translated that algebra into a set of mathematical calculations and translated those arithmetic operations into computer codes. Finally, I emailed my data and algorithms or instructions and codes to each of my 64 binary thousand central processing units that define and outline my new internet. The laws of physics are the core of the global climate model used to foresee global warming were discovered 330 years ago. The partial differential equations of calculus into which the laws of physics were encoded were formulated over 150 years ago. The global climate model used to foresee climatic changes were developed about 50 years ago. Climate change is the world's greatest long-term challenge. The large-scale global climate model of the Earth must be chopped into up to 1 billion small-scale models that could be solved in tandem and solved with a one-to-one correspondence with as many processors. The parallel processing of the global climate model is the technique that must always be used to tackle the biggest question that ever faced our planet and hopefully to find a new way forward. The world's fastest computing is where we transform our deepest knowledge of physics, mathematics, and computer science into real-world solutions that bring benefits where they are needed the most. The physical laws encoded into my computer codes were contained within the governing partial differential equations that I invented, as well as the corresponding algebraic partial difference equations that I also invented. The initial boundary value problem of mathematical physics, governed by those differential and difference equations, was my test bed for the world's fastest computing that I discovered on July 4, 1989. Throughout the universe, the laws of physics are the same everywhere in the universe. Throughout the domains of the initial boundary value problems of computational physics, the system of partial differential equations of calculus are the same everywhere in those domains. The system of partial differential equations that I invented and solved is coupled everywhere in the domain. It's nonlinear everywhere in the domain. It's time-dependent everywhere in the domain. And is hyperbolic everywhere in the domain. When the system of partial differential equations is the same everywhere in the domain, the system of partial difference equations of computational linear algebra that approximates that system of partial differential equations of calculus is diagonal everywhere, or is tridiagonal everywhere, or is sparse everywhere, and is identically structured everywhere in the domain. They are the same for each subset of algebraic equations. Due to that sameness in the physics, calculus, and algebra, the set of floating point arithmetic operations also had sameness in every central processing unit or CPU that executed them. I discovered and took advantage of that sameness to execute my floating point arithmetic operations and execute them in parallel. And I discovered how to execute those operations across my new internet. Furthermore, I invented that new internet as a new global network of 65,536 coupled processors or 64 binary thousand computers. Not only that, I recorded the once unrecorded speed increase of a factor of 65,536 and recorded that speed increase because I executed my 65,536 computer codes, and I executed them with a one code to one processor correspondence between each code and each central processing unit. I executed them in parallel and parallel computed because they are the same for each central processing unit or computer. That sameness was the key to my discovery of the world's fastest computing as it's known today and as it's expected to be known tomorrow. Due to the grand challenge problems looking the same everywhere, I could synchronize my email communications that I sent to 16-bit long email addresses. I visualized my ensemble of 1 binary million email wires as the matrix that weaves my 64 binary thousand processors together and wove them to invent one cohesive supercomputer that's a small copy of the internet de facto. I sent emails across my 16 times 2 raised to power 16 bidirectional email wires. Likewise, I visualized those email wires as short wires printed onto circuit boards or as long wires comprised of fiber optic cables. Furthermore, I computed in parallel or at once, and I did so at 2 raised to power 16 or 65,536 central processing units. That was how I theoretically and experimentally discovered how to compress 65,536 days or 180 years of time to solution on one central processing unit and compress that time to solution to 1 day of time to solution across a new internet. That 1 day was across the new internet I invented as a new global network of 65,536 coupled processors that I named a hyperbole supercomputer. In school essays, this new computer is described as the Emeagwali computer that then US President Bill Clinton described as the Emeagwali formula during his White House speech of August 26, 2000. In 1989, it made the news headlines that an African supercomputer genius in the USA had theoretically discovered how to solve a then world record system of 24 million equations of algebra and experimentally discovered how to solve them across a new internet that he visualized as his new global network of 65,536 central processing units. I was that African supercomputer scientist in the news in 1989. The world's fastest computer that computes in parallel or by solving millions of mathematical problems at once arose from our need to make the impossible to solve possible to solve. My contribution to computing is this: I extended the borders of knowledge of computer science to include the world's fastest computing across millions of processors. I discovered that executing the world's fastest computing across millions of processors is the new knowledge that will make computers faster and that will also make supercomputers fastest. I discovered how to solve the most compute-intensive problems in science, engineering, and medicine. I discovered how to solve them across a small internet that's a new global network of 64 binary thousand processors or as many tiny computers. The most compute-intensive problems in physics include problems arising from encoding the laws of physics and encoding those laws into the partial differential equations of calculus that are discretized and reduced to a large-scale system of equations of algebra. Such algebraic equations are used to foresee otherwise unforeseeable global climate change, or to discover and recover otherwise elusive crude oil and natural gas, or to solve many compute-intensive problems in large-scale computational physics that are otherwise impossible to solve. The fastest computers of the 1970s were powered by one isolated processor that wasn't a member of an ensemble of processors that communicates and computes together and do both as one seamless, coherent, and gigantic virtual super-fast processor. The paradigm in extremely fast computing shifted on July 4, 1989, the date I discovered the first supercomputing as we know it today. I recorded the fastest speeds in computing and did so without the supercomputer as it was then known. In 1989, we changed the way we look at the supercomputer. Before 1989, the fastest computations were recorded on a supercomputer that computed with one isolated central processing unit that wasn't a member of an ensemble of processors that communicates and computes together, and as one seamless, coherent, and gigantic supercomputer. That singular processor was the heartbeat of the supercomputer. Before 1989, the established truth in supercomputer textbooks was called Amdahl's law. In the most quoted scientific paper in supercomputing that was published between April 18 to 20, 1967, Gene Amdahl of IBM Corporation wrote that it would forever remain impossible to achieve a speed increase of a factor of 8 and achieve that 8-fold speed up by using 8 central processing units to power a supercomputer. 23 years after Amdahl's law was formulated, it made news headlines that I discovered that the unimaginable to solve is possible to solve, namely achieve a speed increase in supercomputing of a factor of 64 binary thousand, and achieve that speed increase with as many processors. During the 7 decades that followed February 1, 1922, parallel processing was the holy grail of supercomputing. In the 1970s and 80s, to parallel process a large-scale computational physics code and to do so across an ensemble of 8 processors and do so with an 8-fold speed increase was dismissed and ridiculed as impossible. That factor of 8 limit in parallel processed speed increase was enshrined into Amdahl's law that was in the air for decades but was published between April 18 to 20, 1967. Parallel processing executed across 1 billion processors that shared nothing was science fiction to the computer scientists of the 1970s. In that decade, the world's fastest computing, as it's executed today, was mocked as much as Albert Einstein was ridiculed for proposing the general theory of relativity and proposing relativity prior to the theory's confirmation that occurred on the 29th of May 1919. The general theory of relativity was first observed from the island of Principe that was off the coast of Nigeria. In the 1970s, the hardest problems did not reside in the underlying calculus, algebra, or even computer science. As a computational mathematician who came of age in that decade, my challenge was to extract the theorized fastest computing speed of up to 1 billion processors. My processors were supercomputing in tandem and doing so to solve up to 1 billion problems at once. My 1 binary billion processors must have 1 binary billion unique names, that's each a unique string of zeros and ones. A binary billion is 2 raised to power 32, or 4,294,967,296. Trying to program that ensemble of a billion processors and invoking their services without uniquely naming each processor is akin to employing every living person and doing so without uniquely identifying each person by their names. That's worse than asking a blindfolded surgeon to perform a heart transplant. For those reasons, parallel supercomputing was beyond the intellectual grasp of the academic scientists that I interacted with back in the 1970s and 80s. So I was not surprised when I read the June 10, 2008 issue of the New York Times, where Steve Jobs was quoted as telling the Apple's worldwide developers that, and I quote, the way the processor industry is going is to add more and more cores, but nobody knows how to program those things. End of quote. Steve Jobs continued, quote, I mean 2, yeah, 4, not really, 8, forget it, unquote. To invent the parallel supercomputer is to record the once unrecorded speeds in computation and record them while solving up to 1 billion problems at once and with a 1-to-1 correspondence with as many processors, and to solve those problems when the likes of Steve Jobs of the computer world and the likes of Seymour Cray of the supercomputer world said that it would be impossible to solve 8 problems at once, or impossible to parallel process across 8 central processing units. The likes of Steve Jobs mocked and ridiculed parallel supercomputing as pure ivory tower silliness that only belongs to science fiction. On July 4, 1989, their mocking stopped when I recorded the world's fastest computing across the world's slowest processors. The most powerful supercomputer cost the budget of a small nation. It's bought because the fastest supercomputer gives meaning to life. The fastest supercomputer makes the world a better place and enables humanity to become more knowledgeable. The computer of today was the supercomputer of yesterday. Inventing faster computers proves that humanity is progressing in the right direction. A faster supercomputer, increases our level of civilization and enables our children to do better than us. Thank you very much. I'm Philip Emeagwali. Thank you. Thank you.
Insightful and brilliant lecture.